In this video, we are going to study combination without ordered sampling and with replacement. Actually, it is enough to say combination with replacement because combination always means that there is no order of the sampling. We are going to derive this formula here, and let's start. The question is, find the number of 3-digit sequences that can be formed using the digits 1, 2, 3, 4, and 5 with no order and with replacement. So here we have 5 objects from 1 to 5, and the resulting sequence could have repetitive digits such as this sequence where 1 is repeated twice, 4 is repeated twice, 2 is repeated 3 times, and also we are going to have sequences with no repeated digits. So we have here 2 rules of withdrawal. The first rule is replacement is allowed, and the second rule, order of digit is not important. So sequence 1, 3, 2 is equivalent to sequence 1, 2, 3, and both of them will be counted only once. The first step is to map a sequence such as 1, 3, 3 into a vector as follows. So this sequence is mapped into a vector. In the first component here, we are going to write the number of times digit 1 occurs in the sequence. So it occurs 1 time. In the second component, we are going to write the number of times digit 2 occurs in the sequence. We don't have digit 2, so it is 0. In the third component, we are going to write the number of times digit 3 occurs in the sequence, and that is 2. So it's 3 here is repeated twice, so we write here 2. And in the fourth component, we are going to write the number of times digit 4 occurs, and this is 0. And in the fifth component of this vector, we are going to write the number of times digit 5 occurs in this sequence, and that is 0 again. So now we mapped 1, 3, 3 into a vector of 5 components. Why 5 components? Because the objects we are dealing with are 5. So we are mapping all generated sequences composed of 3 digits into vectors. Now, what is the most important characteristics of this mapping? So let us take, for example, a sequence with 3 different digits, just as this sequence here, 1, 4, 3. It will be mapped into this vector 1, 0, 1, 1, 0. Let us change now the order of these 3 digits. We are going to get the same vector. Let us change it again and again and again and again, and all these sequences are going to be mapped into the same vector. So this is the most beautiful characteristic of this mapping, and the reason why that digital sequences with different orders are mapped into one ordered vectors. So what does that mean for our counting issue, for our counting problem? It means that vectors disregard order of mapped sequences. So what does that mean for the counting? It means that counting ordered vectors will be equivalent to counting the digital sequences without order. So this is the beauty of this transform. If we count these ordered vectors, we are going to be counting the sequences without order, and that's exactly what we need. So let's have a look at some mapped sequences, such as the sequence 1, 1, 1. It is mapped into this vector. So 1 occurs 3 times, so we have here number 3, and 2, 3, 4 and 5 do not occur, so we have all here are all component here are 0. And let's have a look at other mapped sequences just to see the beauty of this transform. So now we are going to map ordered vectors into partition and circles. What is the reason for that? We will see soon. So all these sequences are mapped into vectors. The first step is to map the separating comma into partitions. So for each comma we have corresponding partition now. And the second step is map the number of digit occurrence into circles. So for example, here we have 3-digit occurrence is mapped into 3 circles, 2-digit occurrence is mapped into 2 circles, and 1-digit occurrence is mapped into 1 circle. We will not map the digit 0 here into anything, and the reason why is the non-digit component of this vector give full representation of the sequence, so we don't need to map 0. So far we mapped the digital sequence into a vector. So this digital sequence is mapped into this vector here, and we mapped this vector into partitions and circles. Now we will map these partitions into letter P, and we will map these circles into the letter A. So finally we map this sequence we want to count into an ordered word, and this word has the size of 7. So we have 1, 2, 3, 4, 5, 6, 7, and this word has 4 identical letters and 3 identical letters. We can see now how different sequences are mapped into different ordered words, such as this sequence here. So this sequence is mapped into this word, and this sequence here is mapped into another ordered word, and this sequence here is mapped into another ordered word, and so on. So now let us summarize what we did until now. What we did, we mapped a digital sequence such as 1, 2, 3 into a vector, and after that we mapped the vector into a sequence of partition and circles, and again we mapped the sequence of partition and circles into words such as this word. But we have to remember the following fact, and that is digital sequences with different orders, such as the sequence 1, 2, 3, 3, 2, 1, 2, 1, 3 are all mapped into one unique ordered vector. So what do we conclude from that? We conclude that the number of generated digital sequences without order is equal to the number of ordered words of this form here. So now the question is, how many ordered words of this form do we have in order to solve our counting problem? To know the number of 7-letter ordered words that can be formed using the letters of the word with 3A and 4B, we write these letters into a list, and we find the number of identical letters. We have A equal to 3 and B equal to 4, and the total number of these letters is 7. And then we apply the formula of permutation with identical letters. So we apply this formula: permutation of 7 objects taken 7 at a time and in order with 3 and 4 identical items is equal to 7 factorial divided by 3 factorial times 4 factorial. In the permutation formula, we have 4 factorial. What is 4 factorial? It is 7 minus 3 factorial. So if we remember the formula of combination, we realize that this formula is equal to combination of 7 objects taken 3 at a time. But in the original problem, the number of objects we have is 5 and the number of sampled objects is 3. So what is this 7 and what is this 3 in terms of n and r in our original problem? So 7 is equal to 5 plus 3 minus 1, which is equal to n plus r minus 1. And now we are going to substitute that into this combination formula without replacement, and we are going to get this formula here, combination of n plus r minus 1 taken r at a time, and that is equal to, as we did before, the numerator is n plus r minus 1 factorial and divided by, like what we did here, the numerator minus the number of sampled objects. So here we have n plus r minus 1 minus the sampled object, and we get this formula here. So this is the answer we are looking for. So this is the answer to our problem. And this answer is about finding the combination with replacement of 5 objects taken 3 at a time, and that can be found by applying this formula. Notice that this formula is also equal to combination without replacement of 7 objects taken 3 at a time. So we have here a very beautiful transform from permutation to combination without replacement, and finally arriving at combination with replacement. This is the beauty of mathematics and the beauty of this transform. So we are going to write this in precise form. We are going to write combination, and we are going to write this annotation here as r to distinguish that from combination without replacement. So here we have combination with replacement. If r is not here, then this combination is without replacement. So we read it as follows: combination with replacement of 5 objects taken 3 at a time, or combination with replacement taking 3 objects out of 5, all means the same. And now we arrive at this final formula, which is the answer to our problem. So now let's read this formula here precisely. We have combination, which implies no order, with replacement, or with repetition, or with return, and all of these sentences means the same thing, which means that letter in the generated sequence can be repeated of n objects taken r at a time, and r is the sample size or the sequence size. So we read it as follows: combination implying no order with replacement of n objects taken r at a time. Now the conditions according to which we can apply this formula of combination with replacement. The first condition, objects are defined over a set, and the second one, no order of object, and the third, with replacement of objects. So objects are generated with replacement, and now finally we need to know the characteristics of the generated sequence. So the generated sequence size is r, so the number of combined object is r, and r could be 1, 2, 3, n plus 1, n plus 2 to infinity. So in this case the generated sequence size can be unlimited. That is contrary to combination without replacement. And the third thing is, portion of the generated sequences has repeated objects and the other portions do not have repeated objects. For an example, if we have a sequence of 1, 2, and 3, none of these objects is repeating, but if we have a sequence such as 3, 3, 1, the object 3 is repeated twice. Thank you for listening and have a good day.